you need to use in Kelvin values. Okay, so we will discuss our organic question. So the idea is very straightforward here again. Okay, so the compound A exhibit optical isomerism and has the molecular formula C7H16. You can see, you all see the board, right? Yeah. So because I need to look at the question. So the first thing is you have given C7H16, which means you need to first try to understand whether this is a saturated compound or not. So you know, if that is an alkane, when you have Cn, it should be 2n plus 2. So if you have C7, it should be 7 into 2 plus 2 means it should be 16. C7H16, which gives you the idea this compound is an alkane. That is first point. Second thing is, one might think this can be like a benzene compound. So if you think this is an aromatic compound like this, automatically this should be substituted somewhere to show the optical isomerism, and this entire part will be C6H5. So if you reduce C7H16, there will be C1 like H, how much? H11. So there should be a carbon bounded to this and it should have 11 hydrogens, which is not possible. So which gives you the idea this is not an aromatic compound. So typically this is an alkane which shows optical isomerism, right? So draw two possible structures for A which are not enantiomers. So enantiomers means not are mirror images like L and D. They are asking, don't draw L as one structure, don't draw D as another structure. L and D are typically mirror. Not enantiomers of each other, don't draw L in the boxes given below. So we need to find two structures for this formula which are optical isomers and which are not enantiomers. So C7H16. Okay, so we will start from our chiral center. So I will put like this, one carbon which is our chiral center, and I will draw one CH3 like this, and maybe CH2, CH3 like this. So I have used 4 carbons. And yes, I can use another CH2, CH2, CH3. So 1, 2, 3, 4, 5, 6, 7, and I can put hydrogen here. Okay. So you can see there are 4 different groups. So I drew this in the simplest way. What is the simplest way? For one position, I put hydrogen. The other position, I put 1 carbon. The other position, I put 2 carbon. And the other position, I put 3 carbon. So this is an optical isomer. This is our chiral center. Okay. So what would be its enantiomer? The other one, which means this, you think this as L. D should be this one, right? Okay. But they are telling you can take this as one structure, but you take, no, you cannot take this as the other structure. Okay. What you have to do here is we have to somehow manipulate this skeleton to get another structure. That is the idea. So this cannot be the other structure because it cannot be enantiomers. So how can I manipulate this structure? Can I change something here in CH3? No. Can I change here? No. But when I see this one, there are 3 carbons, which typically gives me the idea. If you have 3 carbons, you can change the skeleton, right? So if you think about this one, just imagine if I do something like this. So I cannot change anything here. This one, instead of this carbon connecting to the first carbon, I would connect this to the second carbon, which gives me the idea. This is now like this. Right? Here it is connected to the first carbon. I am now connected to the second carbon. That is this. So now this one also still optical. Right? So this will be my first structure and this will be my second structure. According to that. Right? And the second question asks, now these are not enantiomers. What I have changed here, I have changed the skeleton. So if you remember about your isomerism, right? If you remember about your isomerism, so in isomerism, you have constitutional or structural isomerisms and you have stereoisomerism. So in stereoisomerism, we discuss about optical and geometric isomerism. In constitutional, we have chain, we have position, and we have functional group, right? So here we have changed the chain because this is this one, then this is we have changed the structure. So now in the second question, they are asking about what is the relationship between these two, the isomeric relationship. The isomeric relationship, that is what they have asked. State the isomeric relationship between these two structures that you have drawn. Okay, these two are optical isomers, so they are stereoisomers. So you cannot compare these two. You cannot tell this is stereo, this is stereo, because both are same. What is the change? The change is the structure. The chain isomerism is change. So typically the isomeric relationship is these two are constitutional isomerism or structural isomers. Okay, this one and this one are structural isomers. Okay, so you know one of the structures, you know the other one, and the relationship is structural isomers or constitutional isomers. Okay, now they are telling a different story here again. B and C are optically inactive compounds with the formula C7H14. Both B and C exhibit geometric, but B and C are geometric and not geometric. B and C are not geometric isomers of each other. So this gives another idea. One structure cannot be cis, the other structure cannot be trans. What is that? That is the meaning of B and C are not geometric isomers of each other. Catalytic hydrogenation of either B or C yields the same compound, which means it also again gives the idea the skeleton of these compounds should be very similar. Otherwise, catalytic hydrogenation will not give same compound A. So the first point again from this equation, this statement, you can decide. Okay, so the idea is now here they have given C7H14, which means now you need to understand this is a alkene, because alkene, the formula goes like CnH2a. So which is in this case, right? That is the idea of this one. And the second thing is, since these are alkanes, right? These are alkenes. And if it is going to show geometric isomerism, B and C is going to show geometric isomerism according to the statement, which means across the double bond, it should have either hydrogen or either CH3 or either CH2, CH3. I cannot draw another one because it should be more than 7 carbons then, right? If we draw more, 3, 3, 6, 7, 8. So I cannot go more. Okay. So if this structure is going to show geometric isomerism, since this is an alkene where it only can have carbon and hydrogen in their structure, the geometric isomeric compound should have hydrogen across the double bond showing cis and trans configuration, or 2CH3 group showing cis and trans configuration, or 2CH2CH3 compound showing cis and trans configuration, right? Then if I try to use this one and try to compare the structure, whether I can form a certain structure or not, we will see. So here I have two carbons and two hydrogens. So remaining C7H14 means I have put C2H2. So typically I can put C5 and H12. So I have to put 5 carbons more. So I can put like CH2, CH3 here, 2 carbons, and here 3 carbons, CH2, CH2, CH3, right? See, this will show now geometric isomerism because there will be a cis configuration and trans configuration, right? Let's take this one. CH3. So here I have used 4 carbons, which means I can use 3 more carbons. So I can put one hydrogen here and put the other one here, CH2, CH2, CH3. 1, 2, 3, 4, 5, 6, 7. Hydrogens 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this can be another one. And we will use another one. CH2, CH3, CH2, CH3. So 1, 2, 3, 4, 5, 6. I have used 6 carbons. So this could be CH3 and this could be this one. Right? So I have 3 structures. Right. Now, what is B and C? That is the important part here. According to this, how would you decide B and C? Because I have 3 structures. The important point here is they have mentioned this one. What is it? Catalytic hydrogenation of either B or C would give same compound A. Okay. So that is the important point because we already know what is A. Right? We already know what is A. So if you remember about our A, it was like this. This is one of the compounds of A, right? So typically you should know. Okay. So typically you should know what is A. Sorry for the inconvenience. I have to put the charger. So you should know how to predict this structure. Now think about the catalytic hydrogenation of this one. For an example, what you will get here is these 2 will be converted to 2 hydrogen, right? And here it will be 2 hydrogen. And here it will be 2 hydrogens. So based on this, right? Based on this hydrogenation product, you have to predict which is A. That's all, right? So I will again share the screen just to follow up. So this is the idea. Catalytic hydrogenation of either B or C yields the same compound A. So you know here 2 possible structures for A, we have already drawn. So it should be formed like that. Okay. And draw the structure of A, B, and C. Okay. Now we will see whether from these three structures, when you form the catalytic hydrogenation, what is the same compound that is formed, right? So typically, I will stop sharing again. You can see the board now. So see what are the compounds which are similar in these three. So this one and this one, are they same? Here CH2, CH3, CH2, 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 CH3. Now this is like a linear chain, right? This one CH3, CH2, CH2, CH3, CH2, CH2, CH3. And here CH3, CH2, CH2, CH3 is a bunch. So you have this one. So what do you think about this? It should form A, which forms, what is the important criteria for this? It should form optical activity. So when you think about this, but here it should also show geometric isomerism as well. Okay. So if you think about the typical information that you should know here, I will quickly go through it. Okay. So the idea is, if you consider about these two structures, which it is possible, you can clearly see when you think about this one, there are two hydrogens. Okay, for the geometric isomerism, there is no problem in that. But when you do the catalytic hydrogenation, it gives no chiral centers. That is the idea. It gives no chiral centers, which means cannot be. That is first idea. The second thing is, come here, right? You come here. Think about this structure and tell me whether this has any chiral centers. Here, this carbon, you can see there are two hydrogens. So this is not a chiral carbon. This will be no. Here you have CH3 and you have CH2, CH3 and you have CH2, CH2, CH3 and hydrogen. Yeah, nice. So here this is a chiral center. Yes, this can be A. Can understand, right? And here again, when I compare this one, when you think about this carbon, it contains hydrogen, CH3, CH2, CH3 and CH2, CH3. So this carbon typically cannot be a chiral center. And this carbon itself cannot be a chiral center, which means this gives me the idea there is a problem with this one. Okay. So what is the problem with this one? Think about that. What is the problem? Can you just imagine what it can be based on the structure that we draw in previously? Because if you imagine about this one, okay, think about this structure. Okay, so this is CH2, CH3, which is pretty similar to here, and there is CH3 and there is, okay. Now, what is the overall idea about this thing here is, if you have this geometric isomerism, which is forming according to these two groups here, and this, this CH3 groups that is forming, what is the typical idea of it? When you do the catalytic hydrogenation, it should form same compound A. But in the previous question, we showed that A can have two structures. But the real structure of A should be either one of these two, because it cannot be two structures. Because according to the second information that we are seeing here, A cannot have two structures because in the meantime they have given the information catalytic hydrogenation should be yielding the same compound from C7H14, which gives me the idea A should be one of the structures from this. Okay, so typically if you consider about all these structures, now we will come to the point. Okay, our one of the structures from our question, it should be this one. 1, 2, 3, 4, 5, 6, 7. Sorry. This is one of the structures that we can draw. The other one is this one. Okay, 1, 2, 3, 4, 5, 6, 7. Okay. So this is the overall idea. So when you do the catalytic, I will put this one here just to make sure you get the idea clearly. And now you do the catalytic hydrogenation here. So there will be hydrogen here, and you do the catalytic hydrogenation here. So typically, you can see okay. And you can also see the chiral center here. Okay, so you can see 1, 2, 3, third carbon, there is a methyl group. So 1, 2, 3, third carbon, there is a methyl group, and rest of it is CH2, CH3, CH2, CH2, CH3. So you can see these two compounds are same. Why you see these two compounds are same? Because you need to understand here, when you do the catalytic hydrogenation, it forms this. Now, based on this, what should be our structure of A? Clearly, you need to understand it should be this one with where we had CH2, CH3. So typically, it should be this one. Methyl substitute. Okay. The other one where we changed the chain, like attaching instead of this carbon to this carbon, cannot come because we saw if you draw this attachment here, I explained to you just before, it cannot give you a chiral center when you do the catalytic hydrogenation. That is our problem. Okay. So think about this clearly, right? So this will be our one of the structures B, and this will be C. You can take either both as B and C, either this B, this C, or this B, this C. And typically this will be our confirmed structure of A. Because in the first question, what they are telling us is to find whether one of the is A or B. And there are two structures for A. And in the second part, what is their given information to find the exact structure of A, because first one had two structures. Based on the information that they have given in the second one, now they are trying to find what is the real structure of A. So that is the idea that you should understand. So we will again come back to the question. So the idea is we draw two structures for A first. And based on this information, now we decide this structure was the real structure along with structure B and C. Okay. And then you can name it very easily according to the IUPAC. But B and C can be interchanged because I told you whether you can do this one or this one. It is not a problem for you. Okay. So this is a nice question where again you see a little bit of optical and geometric. So if you remember about our 2012 discussion, there also you had this connection between optical and geometric. So try to go through this and try to get the concept that we have used here. First thing that I used here is check whether this is an alkane. And before that or after that, you can check whether this is aromatic compound or not. Okay, this cannot be aromatic because it cannot show optical. Then point by point, try to get the idea. This is optical isomerism. So draw one of the optical isomerism. Try to change the structure and find another one. So you can draw two structures. That is the idea. Second thing is the relationship. It is straightforward. And third, from the data given, you can predict. Here also I started with the formula. So it should be an alkene, okay. And they are telling B and C should exist. Geometric. So I drew all the possible structures. In fact, I do 3, which only 2 are okay. Because why? One of the structure is a problem where you cannot have chiral centers. So it is a problem. Then based on that, we decide the real structure of A. Then you can name according to IUPAC nomenclature, right? So moving on, this is part B. So this is now it should be very straightforward now. If you add HBr, it should give CH3CHBr. And if you add alcoholic KOH, you know HBr is removed. And NaNH2 liquid ammonia. So when you remove alcoholic, it clearly should form like a alkyne compound. And when you add CH3CH2Br, it will form the alkyne along with CH3CH2Br combined, right? So typically you should be able to write down this scheme. So if you want to use the board, I will check the question as well. So because it will be easy for me to draw. Yeah. So the idea is this.
Pink microphone.
Who is talking? Okay, so CH2Br, right? So typically what you have to do, you add HBr. So here there will be CH3, CHBr, CH2Br. This is one. He's talking. Okay, so it's right. Okay, so you add the alcoholic KOH. Typically, there will be 2 elimination steps happening, right? So it will form Br with this H, this Br with this H, and it will form this one. Okay. Then you add the NaNH2 liquid ammonia. So I have already told these terminal hydrogens are acidic. They can react with this sodium NaNH2 ammonia or either sodium itself. So there will be this sodium forming. And when you have this alkyl halide CH3CH2Br, this can attack this Br and remove. So typically the final product will be carbon added to CH2CH3. Okay. So these are the 4 products. 1, 2, where is the other one? PQRS. So P is this one. Q is the triple bonded one. That is this one. We manipulate the structure earlier. That is this. This is the R and this is the S. So 4 structures. And what you have to do is classify the reactions according to the substitution or elimination or these mechanisms. So reaction 1, you know, it is a electrophilic addition reaction. This is elimination. So this is substitution, nucleophilic. This is also nucleophilic substitution. So it is straightforward, right? So this is not much that you need to know very quickly. That if you know the reaction, you know the you know the product, you know the mechanism, and they have also asked for the mechanism for the reaction one. So this is a typical mechanism. We already I think we have discussed this many times in MCQs as well as one of the structured essay questions. So you can quickly write down the mechanism. I think I don't want to explain this mechanism. So this pi bond should attack H plus and Br minus will be removed. First it will form the carbocation, then Br minus will attack this carbocation and form the product. Okay, so fourth question number 4. So I will again share the screen here. Okay, so this is what I am telling. These are the 4 structures: mechanism, reaction 1. Draw the structure of the product T when reaction 1 is carried out in the presence of peroxide. So I have already told that if you do this reaction in the presence of peroxide, you are going to get the anti-Markovnikov product, right? For an example, so this is our Markovnikov product where hydrogen is added to the maximum, and anti-Markovnikov means it should be the other one. Like we should have CH2Br here, and here it should be CH2Br. So this should be your product T. It has been found that T is also formed in reaction 1 as a minor product. By considering the mechanism of the reaction, explain why the major product in reaction 1 is P and not T. So you can explain that according to the stability of the carbocation. So because in the first step, you see here CH3 CH2Br. This is the carbocation. So this is a secondary carbocation. So if you think this product is formed, this is the carbocation that it should form. So basically you can write down these 2 carbocations in the box. And you can see this is a secondary carbocation and stable than this one, primary carbocation, less stable. Okay, can understand. So the idea is secondary carbocation is more stable than a primary carbocation. So that is why this becomes the major product and this becomes the minor product of the reaction, right? But in the presence of peroxide, this product becomes the major product, because in the presence of the peroxide, the reaction happens at a different way, in a different way, right? Okay, so here also they mention award full marks if you just like argument for the argument, right? Secondary carbocation is stable than this primary one without giving these 2 structures.